Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Abir. He will be speaking on locality sensitive hashing in Fourier frequency domain for soft set containment research. Professor Dey is an assistant professor in the Department of Computer Science and Engineering at IIT Bombay. His current research focus is designing machine learning models and methods for structured objects, for example, graphs and sets. He is a recipient of various research awards, including Indian National Academy of Engineering Young Engineer Award, Professor Kriti Ramaritham Award for Creative Research, and Google India PhD Fellowship. He did his PhD in Computer Science from the Indian Institute of Technology, Kharagpur, and was a postdoctoral researcher at MPI SWS. Before we move on to the talk, we would like to request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box. We'll relay your questions. Over to you, Professor.
Okay, thanks. Thanks for the invitation. I will talk about locality-sensitive hashing for soft set containment search. So there are a few jargons here, starting with locality-sensitive hashing and then set containment search. In the original title, you will see also something on Fourier transform. So I at least omitted that one from the title, which might look a little simpler. So we'll describe all these jargons one by one. So this is a joint work with Indradumna Rishi, who are students at IIT Bombay. So Indradumna is a PhD student and Rishi is an undergrad who is now at Stanford. Professor Showman, who is my colleague, and Professor Anirban Dasgupta, who is a professor in IIT Gandhinagar. Okay. So what is set containment search? So suppose you type something in Google. You write a text, and you can imagine that on the backyard there is a large amount of corpus items called web pages, and the Google has some algorithm which will return the relevant items corresponding to this query that you type. Okay, so and you see that that set of web pages are kind of constant, right? So it's kind of dumped. You can assume that it's reasonably static for the time being. And the moment you put some query, the task is that you have to find the similarity between the query item, the text that you write, and the document that is stored, or the web page, or the content of the web page that is stored in the backend. So here we have similar setup, except that we don't type something in terms of text. We rather have a set in query and in corpus. So now we have a corpus, which is analogous to the set of documents in the backyard, which is static and from which is supposed to be retrieved, because like the relevant subset of which is supposed to be retrieved corresponding to the query. This every such document is a set. Okay, and the query is also a set. And the task is that I give you a query, and you have to find k superset of xi's efficiently, which is critical. This efficiency retrieval is very critical here. That's the entire focus of this one. So that q is a subset of x. So you could see here that only the first item is a superset of q, so that is relevant. And for all other items, you could see that q is not a subset of x2 or x3, so they're not relevant. So in principle, it should just return x2. Okay. So why we are bothered about this particular problem? So there are a lot of applications, starting with, let's say, top K graph retrieval. Let's say you have a set of molecules and you want to find a motif present in the molecules. Okay, you have to return, let's say, a bunch of molecules who are aromatic. That is, in some sense, they contain the benzene rings, right? So here the problem is find top K supergraphs xi such that Q is a subset of xi. Okay. So another application is that the find k images efficiently such that the objects in Q in content is xi. So that's also a set containment search. So you could see that I give a picture of the tiger, and you are supposed to find a picture of tiger, a set of pictures out of a corpus of images, so that each of these contain a tiger. So it can contain other animals, I don't care, but what I need is that everyone should contain a tiger. Okay. So now the point is that there can be cases, in fact most practical cases, you don't exactly need that particular object that is present in the query. Something similar to the one that is present in the query will also work. For example, I give a set of images and I don't care whether it's a tiger. If it is leopard or jaguar, I'm also okay, for example, depending on the context. So here the task is that I give you an image query queue and find k images xi efficiently, again, which is critical, such that the objects in Q is approximately contained in xi. It's approximate containment. Okay. So this is called the soft set containment search, that I want an approximate containment. So to do that, what I say is that I kind of represent Q, because now there is an approximate containment. We need some kind of smoothness in the space. So we want that the Q set, the query set, is basically represented as a vector. And there are a lot of work on how to represent set in a vector using neural network. For example, you can think of deep set transformer. So they kind of represent a set in the vector spaces. By proper training, you can make sure that the two sets are similar if their items are also similar. Okay. So Q is contained in, so Q is represented as a vector Q vector, and X is represented as a vector X. Okay. And then what we say is that now we give an approximate notion that Q is contained in X. Approximately means that the vector Q is less than or equal to X in an approximate manner. So and this inequality is entry-wise. Okay. So is that clear up to this, the motivation and the setup? If it is not clear, I can slow down or take up questions. Any questions? So we have plenty of time as of now, so you can ask questions.
Oh, this is good, except that for this set, what do you mean by approximation?
Yeah, so what I'm saying is that by approximation, I mean like when you are going to the vector space, you really don't know that whether you really want a mango in a very ripe mango or in a green mango. So what we say is that, let's say you have some elements in Q which are close to some elements in X but not exactly same. I'm okay with that. So Q is less than or equal to X. This approximately means, so if you represent that in the vector space, we say that, hey, I do not need the exact item matching, but what I need is that if you represent that is a vector space, they should be similar. Okay. So
I got it. And but you still should be a member, right? That means that the type of so Q supposes certain elements, and a close enough approximation should be in X, but everything in Q should be in X, right? I mean, an approximation of them should be in X, right? It's not
yes,
it's not
yes,
acceptable that a like Q intersection X is non-empty, but not everything is there. That's not okay.
That's not okay. That's not
Okay.
okay.
Okay, that's all. Thank you.
Yeah. So all I mean is that it should be set containment. It should be totally subsumed by the corpus set, but it should not be the case. It may be the case that items are not exactly matching, but I'm fine with that. Okay. So now if you want to consider this similarity, you have to consider a distance. So the distance means that if q is less than equal to x, if this condition is sort of violated, then I add a penalty. So what we say, we compute a hinge distance, right? So you just take the difference between q and x and apply a hinge. If some elements of q is more than some elements of x, you say that there is some distance, it's not exactly subsumed, so it's a similarity between q and x. So now we'll deal with similarity, because now we are going in the continuous space. So similarity between q and x is now minus of sum of elements of q and x, and then ReLU applied on top of that. Okay. Okay. So if this is clear, because I'm able to see the screen, not the faces. So yeah, so I'll move ahead. If you have any question, feel free to stop. Okay. So now the problem becomes that, again, like given a query q, find top k sets xi in terms of similarity between q and x. So basically you have to sort them in terms of the similarity in an efficient manner. Okay. So that's the goal. So this is, let me go to here. So this is quite well-known problem in information retrieval, that I give you a query and you have to return top 5 pages in the search page which are relevant to my query. This is something that we want, and the task is that you basically compute the score between the query and each corpus document and sort them in a decreasing order, right? So the problem is that there can be millions or trillions of web pages. There should be some technique, because otherwise there will be real-time queries in every minute, and then you have to do this for 1 million or trillion times for every thousands of query or hundreds of query that come in every minute, right? So the task is that you have to basically save this pairwise computation. So possibly you are not allowed to compute the similarity between q and x for all possible x. You should have some mechanism to pre-select these x items, so that given a q, I automatically know I have to go to that particular set of x rather than all sets of x, so that I can compute the similarity between q and x, and I can restrict to that particular subset. Yeah. So there has been a lot of work on this, starting from, let's say, 1998. Okay. So, but the point is, people have been trying this for cosine similarity, where the q and x are similar in terms of the vector direction. So what is the solution there? That I give you millions of xi's. Okay. So I basically represent this unit vector xi by norm of xi's. Whatever number of documents I have, the corpus items, possibly large number, let's say 1 million, in the hyperspherical space. Okay. And then I have to index them in buckets, and it's a one-time computation. That means that before actually triggering any query, you do it for once, and then find the bucket B for each query q. That's what we do. So I index them in the bucket. So now give me the query, it should be able to quickly find out which bucket I should go and return top k items in the bucket B. And funnily enough, you look at that, it is basically saving the computation, because the computation for each query is now restricted within the bucket instead of the entire corpus items. And yes, you have to process the corpus items for only one time before any query comes. That's correct. But after it is done, the moment I trigger a query, I will just go to the bucket and return top k items in the bucket B. Okay. And when I compute the top k items in the bucket B, I believe that the number of items in the bucket will be much smaller than the entire corpus items, so that I can restrict my pairwise computation, the pairwise computations within the items of that bucket only. Okay. Yeah. So any question? I'm still audible, right?
Yes.
Okay. So the question is how to construct these buckets. So the basic idea is that you basically draw random hyperplanes on X. It's quite standard. Basically, you draw W1s on random hyperplanes. Okay. And then you construct some bits. Okay. Some bits which is basically sign of W transpose X. So basically it's projecting X with basically apply W transpose on X and compute the sign. So it's just one bit. So essentially what you do is basically you say that, I have to split the entire hypersphere into random hyperplanes. So this is called random hyperplane methods. So I split the entire corpus into random hyperplanes, and then I look at the angle or the area in which that particular X lies, and then I actually characterize each bucket using the sign of W transpose X. So it basically says that which regime X is lying. Okay. And the bucket ID of X is basically H of X. That's all I do. Okay. Is it clear until this?
Yes, please move on.
Okay. And it has been shown that this probability between HQ and HX is basically directly related with the cosine similarity between Q and X, that is this given similarity. Okay. So basically this kind of algorithm provides some theoretical guarantee, which is clearly evident from this. So for each bucket, the bits will remain same if their similarity between Q and X is 1. In other words, the probability will be high if the similarity between Q and X is high, and vice versa. Okay. But the strategy holds only for cosine similarity. Right. So we have a different and more complex and very, very complicated notion of similarity here. So the first challenge here is that asymmetric similarity. So cosine similarity has a certain structure that gives you that gives you an hyperplane. Okay. And which admits theoretical guarantee. But we have not only a different similarity, which will prevent us from using that kind of random hyperplane method, but also the fundamental characteristics of a similarity function, which is symmetry. That means if you exchange Q and X, the similarity will remain same. That's not the case, because we are looking for Q being a subset of X, not X being a subset of Q. And Q being a subset of X does not imply that X is a subset of Q. So similarity between Q and X is not similarity between X and Q. So this is an asymmetric similarity. Okay. So unlike cosine similarity, this case is asymmetric, which is a fundamental problem. And then what we try to do, that somehow we have to characterize this similarity between Q and X as a cosine similarity between two asymmetric function phi1q and phi2x. So that's a critical thing here. Again, if you want me to repeat, or if you have any question, feel free to ask. Any question by now?
Can you please repeat the last part? How the phi is related to the similarity?
Yeah. So what we need, let's say, is that we have a hinge distance, and this is not cosine similarity, but somehow imagine that we want to you want to transform Q into some other domain phi1 and X into some other domain phi2. And basically I give a Q and I give you an X and you apply phi1 and phi2 so that this hinge distance is same as the cosine similarity or the cosine distance in that phi1 phi2 space. So that if you ask me to apply locality sensitive hashing for hinge distance, I will apply the cosine similarity based LSH on phi1 and phi2, which is already proposed and well established.
Okay. Okay. Thank you.
Okay. So now our task is that we basically reduce the similarity between Q and X directly to the cosine similarity between phi1 and phi2. Okay. So here our goal is that we have to apply a Fourier transform of it, and I'll show how can it be replaced as a dot product. So this has been inspired from the well-known 2017 Test of Time Award paper by Rahimi and Recht, which is random features for large-scale kernel machines, which were published in 2007. So imagine that we express this in the form of a Fourier transform. There are blockers, but let's say we can express it this way. Okay, we just apply a Fourier transform, and then you can actually take this e to the power minus iota omega k and e to the power minus iota omega xk. You can separate them out, right? And you can take that as a dot product. It's not still cosine similarity, but this will give you a directly as a dot product. So you multiply, let's say s is positive for some cases, as you just take square root of s into e to the power minus omega k into q, and square root of s into e to the power minus I omega k xk. So now there are two functions which becomes a function of q and function of x, and they are totally decoupled, right? And thus you express them as a dot product. And then you design a probability for important sampling. Okay, so the problem is that the moment you apply this dot product, it's still not over, because you can see this is a dot product in the infinite dimension of omega. So imagine you want to express this in the form of dot product of two vectors, correct? The integration will prevent you from doing that. Instead, if omega has been discrete, you could have done it with you have a double summation, you could have done that way, but the integration will prevent you from doing that. So suppose we could discretize this. So how should I discretize it? I just use a probability distribution. Okay. So just design some probability for uniform sampling and you convert this way. Okay. And now you have an expectation. So you basically sample, right? And compute the Monte Carlo estimate of the dot product and get this similarity out. So now it's clear to everyone, or should I repeat?
It's clear.
Oh. Okay, but there is some problem. Those who know Fourier transform, they know that if I have a ReLU like this kind of function, I really cannot compute a Fourier transform because this is not absolutely integrable. Okay, so what we do is basically we convert into a similarity function and truncate them between 2 points, which is minus t and plus t. And this is absolutely okay, because you can assume that each element is bounded, and you can only restrict your treatment of this analysis within that bound by safely keeping any points lying outside that bound to be 0, because those points will never appear. Okay, and then you just invert this, because this is the distance d of qx, and you just apply some kind of monotone decreasing function, which is this, which is kind of lift by amount of t and truncate by minus t to plus t. And now we can compute Fourier transform of similarity. Okay, and the Fourier transform will look like this, and you could see that the Fourier transform actually exists from minus infinity to plus infinity, and it also exists in 0. So yeah. So now we get S in this way. In the step 2, again we convert into a dot product in the integration space. So you have a complex vector now, complex in a complex sense, but it's complicated looking vector, but it just comes from algebraic calculation. You don't have to worry about it. Okay.
Sorry, can I ask a question? Maybe if you go to the previous slide.
Correct. Yeah.
Maybe even one more slide. Yeah. So I didn't quite, maybe I missed something. So this dqx is sort of clear, right? The what you have written. And from there, how did you go to this sqk minus xk? This
So first of all, take minus of d. Okay. So you can think that as a kind of similarity, and lift it by
always the minus of that and shifted by t a little bit on the x-axis. Yeah, I can see that, and then you have truncated it. It seems.
Yes.
And truncated not only in the time, also over. I mean, not on the x-axis, also the y-axis.
No. Truncation will not. The moment you automatically truncate in the x-axis, it will only lift t because it's an x equal to y curve on the right side.
Okay.
So the moment you truncate into t, it will automatically truncate in the y at the level t. And
no, I know, but to the left side of the x-axis, because that could have kept going, right? Because the q minus x takes infinite value, right? I mean, it can keep increasing.
Yeah, correct. So we truncate it to minus t because the point is that again it will not be Fourier integrable. The reason why we truncate it and it does not destroy the the criticality of the problem, you can assume that q and x in the real life is always bounded. So beyond a certain point, you will not get any data points. So you can restrict your analysis only between minus t and plus t, and that can be computed from the data.
Thanks, Abir. Thanks.
Yeah. So now the next step is that, we have to discretize it because we divide by some p omega and multiply with p omega. So the moment we sample based on p omega, you have to scale it by p omega. And remember that you have to basically consider p omega, which integrates to some function which is positive and integrates to 1. So that means that whenever p omega is 0, SQ transpose SX has to be 0. So this gives a p omega, to be proportional to this. This is one of the candidate. Okay. And the candidate is not, again, that if you take the integration of the RHS, it will not be convergent. So we basically limit them between minus omega and plus omega. Okay. So this is, you can think that as a hack, but it still gives some kind of some sort of guarantee. You can look at our paper actually to look at more detail, because depending on omega, the estimation will be more and more accurate. But again, we have to truncate to omega because otherwise you cannot compute to p, since this integration of absolute value of real and absolute value of imaginary will not be finite. Yeah. So finally, after we get this, we can get an approximation of the similarity in the space of fq and fx, and where the norm of each is kind of same. And so you can say that, okay, similarity of q and x is proportional to the cosine similarity between fq and fx. Okay. So now I'm given a distance. From that I have computed similarity, and the similarity is basically now an approximately same as the cosine transform between the cosine similarity between the fq vector and fx vector. So I can directly
these f's are same as the phi you discussed earlier.
Correct. This fq is now the phi 1 and fx is the phi 2.
Okay, thank you.
So now one can directly use the random hyperplane LSH here. So basically what you have to do, you just apply wi's and then apply wj over fx and fq. So you don't multiply on q and x anymore, because now we have a new vector of fq and we have transformed the hinge similarity in the cosine space. And then we actually make this even fine-grained by training it. So that part is a slightly disconnected from here, but we have seen that it improves the performance. That we compute the Fourier transform on this and perform fx and fq, and then feed into two neural networks, phi x and phi q, and then apply cosine similarity between them, which kind of improves the performance. Okay. And then here is something, again, like, for the sake of time, I'll skip, but think about that random hyperplane is kind of data oblivious. Okay. So you always, when you apply random hyperplane, it will be like it will spread across the entire hypersphere. But suppose all your corpus items are localized in only one place, one particular corner, then you cannot actually draw, lot of hyperplanes to separate them out, because all the buckets will take all these corpus items, right? So suppose we want that these hyperplanes should know the data distribution. So to do that, we actually train the hyperplanes. So you could see that, we apply random hyperplane on the Fourier transform, and then apply a tan h. Tan h is basically an approximation of plus minus 1. Imagine that we take a sign there. So we basically take a tan h here, so that you get plus minus 1 bit. And then I get a hash vector and hx and gq, which are different. And then we have some hash specific loss, which kind of maintains this, uniform distributions across the bucket, so that we can really save some time. Okay. So that's the high level overview of this. So coming to the evaluation part, we basically consider each query and corpus item is a set of strings, and the set embeddings of the q and x vectors are obtained using deep set mechanism. And then evaluation, during evaluation, we just try to trade off the retrieval time and mean average precision. So the few things that I want to tell here, that if you see the right axis, the x-axis, that is time, and the y-axis is map, and there are three baselines. One is random hyperplane hashing on the cosine trained embeddings. Okay, that means that you basically train your model using cosine similarity instead of this hinge or our similarity, and then you apply random hyperplanes on top of that. Second, you don't apply cosine similarity, but just distort this score using just dot product. So it's kind of variation of cosine similarity. And some other baseline which is called weighted mean hashing, which is weighted Jaccard similarity between the train embeddings. So basically, think about, there are two sets, right? And the similarity between two sets can be always computed using Jaccard similarity, which is basically the ratio between intersection of two sets divided by the union of two sets. So it's kind of 0-1 similarity. So, and it is symmetric. And there are work on continuous approximation of Jaccard similarity, and there are mean hash mechanism which is applied on this Jaccard similarity based distances. So applied on top of that. So we see there are some improvement. And now we actually give more, we test our model more adversarially, where at the end we always apply hinge in whatever way you hash. So basically you do the hashing, you basically index them in the buckets, but finally when you retrieve, you actually retrieve using the hinge score. But the hashing is based on dot product, weighted mean, etc. We see that the performance, if you look at the difference between the performance, the baseline performance has improved significantly. But what we have seen, that for Fourier hashnet, we could see that you can tune the hyperparameters to transfer them from entire time axis. So suppose I want a map within time 0.02. You can get quite a bit of points for Fourier hashnet, but you will not get the similar level of points for FOURIER or WMH plus hinge. Okay. So this is something that we get, like you just analyze the impact of Fourier featureization and hash code training, and we can see that if we see that with full training with Fourier hash and untrained Fourier hash, it's almost close. It's simply that the difference lies on the phenomena that the Fourier hash without training is basically not spread on the entire axis. There are basically some scarcity of points of high map regime. So if you want a very high map, you may not obtain it that easily, but still you will be able to obtain. Okay. And so this is something else. So it's basically on the hash code trading that I'll skip. So in conclusion, we kind of have locality sensitive hashing for hinge scores. We have a trainable model for hash code trading, and our method can be extended to any shift element scoring mechanism. It's not just hinge based method, but any shift element scoring mechanism. So the future work is whether we can extend such methods for more complex coding functions, and also whether we can use this method for other efficient computation tasks, for example model pruning and etc., rather than LSH. Yeah. So this is over. So I am ready to take up any questions, if any.
Thank you, Professor Dev, for an informative talk. Please feel free to ask any questions if you have. Okay, seems like there are no questions. So if there are no questions, we can close this session for today. Thank you all for joining. Thank you, Professor. Have a great day.
Thanks for the invitation.